principle of mathematical induction. So that is for any mathematical statement, I have to prove when n equal to 1 the statement is true. When n equal to k we assume the statement is true. Then we have to prove when n equal to k plus 1 the statement is true. So then finally we say that the given statement is true for all n, set of all positive integers. Then we see some problems. Okay. Okay, the end of the last class, I am asking one question, that is, what do you mean by prime numbers? Okay, so we discuss I asked one question. So, what are the prime numbers? The students replied that prime numbers means the divisors are only one and itself. Suddenly I raised one question, that is, minus 2 is a prime number or not? So in that case, minus 2 is not a prime number. Some students replied, okay. Now, we are going to see the proper definition of prime numbers. Okay. So today we are going to see the topics of prime and composite number, prime number and composite number. Okay. So prime numbers are the building blocks of positive integer. The meaning of this quote we will see later. Okay, after defining the definition, then we will discuss some interesting points. After that, you conclude that this statement is correct. Prime numbers are building blocks of positive integers. Okay, now we see the proper definition of prime. Okay, that is, what is the definition? A positive integer greater than 1 is a prime number or simply prime if it is only positive factors are 1 and itself. So in the definition itself, we bother only about the positive integer. We didn't bother about the negative integer. So only minus 2 is not a prime number. Okay. So a positive integer which is greater than 1 is a prime number if it is only positive factor. Okay, here we bother about only positive factors. Positive factors are 1 and itself. Okay. Okay, what about the composite number? So a positive integer which is greater than 1, that is not a prime, is a composite number. So I can classify the set of all positive integer. The only factors are 1 in itself. It belongs to prime number. Otherwise, it belongs to composite number. Then suddenly, in your mind, there is a question will rise. So what is the question? Sir, you speaking about positive integer. So 1 is a positive integer. So what about 1? So in that case, because definition is only for greater than 1, what do you mean by 1? That is the remark, the next remark. 1 is neither prime nor a composite number. Okay. Then we will see the examples, some examples. At least you have to remember first 10 prime numbers. What are the first 10 prime numbers? 2, 3, 5, 7, 11, 13, 17, 19, 23 and 29. Similarly, what about the first 10 composite numbers? 4, 6, 8, 9, 10, 12, 14, 15, 16 and 18. Okay. Next, I raise one question. Okay, so today's session oftenly when I going to start one new topic, I raise the one question. That is, you ask yourself whether the question is true or not, or you can able to find the answer for that question. Okay, is there any relation from 1, comma prime numbers, comma composite number, comma set of all positive integer? So anyone try to reply me? Is there any relation? See, so whenever I am asking the question, you have to think about the before question, what I teach you. Okay, you think about that thing, that definitely you can answer me. Okay, so my question is there is any relation from 1? There are four topics. There is number 1, the prime numbers, composite number, the set of all positive integer. Is there any relation from these four? Please reply me, anyone. So see the definition. See the definition. See the remarks. Okay, what is my definition? A positive integer greater than one is a prime number if its only positive factors are one and itself. The condition fails, it's become a composite number. Then one is a neither prime nor a composite number. Okay. Now tell me what is the relation between these four? One prime numbers, composite numbers, set of all positive integers. Anyone? Okay, I will give the answer. Yes, there exists a relation. What is the relation? It follows from the definition that the set of all positive integers can be partitioned into three disjoint classes. That is, my first class is set of all primes, the next class is set of all composite, and the next one is singleton U. So set of all positive integers is nothing but union of these three. So that is our relation. So set of all positive integers is nothing but union of three disjoint classes. Okay. Okay, at least try to answer for this one. What do you mean by factors of a number? Please reply me. The word factor is most important one for the next definition. So please reply me. What do you mean by factors of a number? Anyone reply me? Okay, no one reply me. So what are the factors of it? At least reply for this question at least. What are the factors of 8? Otherwise, what are the positive factors of 8? No one reply me. So this is a simple question. Try to reply me. Then only you will get some knowledge. So already I told that these are all simple topics. You have to get the deep knowledge in these topics. So only I am raising the question each and every session. Okay, so the factors are 1, 2, 4, 8. Okay, why we call these factors 1 into 2 into 4 into 8? That is, 1 into 2 into 4, this is 8, or otherwise 1 into 8 is 8. This calculation is wrong. 1 into 2 into 4 is 8, or 1 into 8 is 8. Okay. Okay, now I give the proper definition. So, what is the definition of factor? Multiplying two whole numbers gives a product. The numbers that we multiplied are the factors of the product. Okay. For example, I can assume 2 into 4 is equal to 8, where 8 is a product, 2 and 4 are factors of the product. Here you can add 1 is a factor, also 8 as a factor. That is not a problem. Then another definition, this is an impact definition. There is an impact in. So a factor divides a number. A factor divide. Already I told that what do you mean by divides? When you divide a number by some other number, the remainder should be 0. That is, when you divide a number by its factor, remainder is 0. So that number is called by factor. I will give some example. What are the factors of 10? What is the factors of 10? 1, 2, 5, 10. When you divide 10 by 1, the remainder is 0. When you divide 10 by 2, the remainder is 0. When you divide 10 by 5, the remainder is 0. When you divide 10 by 10, the remainder is 0. So the factors of 10 are 1, 2, 5, 10. Okay. What do you mean by factor? When you divide a number by its factor, the remainder is 0. Okay, let me at least try to answer for this one, because this experiment is very important for the next result. This next important result, that is a half of the 8-mark theorem. Okay, next result is, let me do one experiment. Try to factorize the following numbers. Keep in your mind, we deal with only positive integers. First, what about the factors of 2? So here I omit the factors 1. Okay, one is always factor for each and every number. So I omit 1. So what is the factors of 2? 2. What is the factors of 3? Simply 3. Okay, because 2 is a prime, 3 is a prime. What is the factors of 4? 4 is not a prime. Okay, 4 is a composite number. Okay. Uh, what is the 4? Factorization of 4, 2 into 2 or 1 into 4. I omit 1 and 4 here. Okay. So what is the factors of 5? Simply 5 because 5 is a prime number. Similarly, what is the factors of 6? 2 into 3. Similarly, what is the factors of because 6 is a composite number. Then what is the factors of 7? Simply 7 because 7 is a prime number. What is the factors of 24? That is either I can write two way 2 into 3 into 4 or 2 into 2 into 2 into 3. So the factors of 24 are 2, 3, 4 or simply I can say 2, 3. Okay. So collection of all factor means you have to say the 2, 3, 4. Simply I can factor means the or otherwise the 2 I can represent in two way 2 into 2 into 2 into 3. Otherwise 2 into 3 into 4. Okay. So from this experiment, can you observe anything about the numbers? I choose 2, 3, 4, 5, 6, 7, and 24. The factors of out of the numbers, the factors of the number, can you observe anything? Here we're dealing with only prime number. Please, anyone reply me. So factors of 2, factors of 3, 5, 4, 5, 7, 6, 7, and 24. When you find the factors of these numbers, when you observe anything, please reply me. Anyone? Sanjay, Vignesh, J, Ujwala, are you listening the class? Ujwala.
Yes, sir.
Mm.
Yes, sir. Sir,
Can you
the
find?
factors of
Mm.
composite number will be product of prime.
Okay. Product of prime. What about the
Prime number.
24? What about the 24? 2, 3, 2 into 3 into 4.
Sir.
Okay, so exactly correct. But I will give the see. Suppose the factors of 24s are 2, 3, 4. In that case, you cannot say that product of prime numbers. Here, product of prime and composite number. So we can say that every integer greater than or equal to 2 has a prime factor. Suppose if we choose any integer greater than or equal to 2, definitely one of the factor must be a prime number. So this is our conclusion from this experiment. So that is nothing but our next lemma. Every integer n greater than or equal to 2 has a prime factor. This is a important lemma because after this we have one theorem. Okay, so that is a 4 mark theorem or sometimes 8 mark theorem. 8 mark theorem means you have to write first this lemma. After that only you have to prove the theorem. Suppose the theorem is asked as a 4 mark problem, the theorem itself enough. No need to prove the lemma. Okay, so only I told that this is an important lemma. Proof of the lemma we will see later. Okay, next time raise one question. So whenever I ask question, you have to ask yourself. Okay, then only you get the clear cut idea about the particular topic. Or okay, my next question. You first I define the prime numbers. Then we see the examples of prime number. Okay. Then next, my question is there any finite number of primes are there? Is next suddenly, so we study one type of numbers early in your mind. There are finite number of finite prime numbers or infinite number of prime number. The answer is no, because the theorems next important theorem is there are infinitely many theorem, sorry, infinitely many primes, not theorem. So there are infinitely many primes. So Euclid is a mathematician. First he proved this statement. So only I write Euclid. So there are infinitely many primes. This is an important 8 marks. So 8 mark means you have to prove the theorem as well as the previous lemma. Suppose 4 mark means you simply prove this theorem alone. Okay. There are infinitely many prime. Proof of the theorem we will see later. Okay. First we will deal with the problem, then only I move on to the proof of the lemma theorem. Okay, next question. This is an important one. How do you check? Okay, sir. We define a definition of prime number. Then we see some examples. Then we check that whether there are infinitely many primes or finite prime. The answer is infinitely many prime. The next question: suppose given a number, how do you check whether it is a prime number or not? There is any technique is possible? That is my next question. How do you check a given 2-digit or 3-digit or 4-digit number is a prime number or not? If we increase the number of digit, it's a little bit difficult. So only I choose only 2, 3, 4. In exam point of view, maximum 4-digit they will ask. Okay. How do you check a given 2-digit or 3-digit or 4-digit is a prime number or not? How do you check? My next question is there any technique is exist? Their answer is yes. That is nothing but our next theorem. Okay. The next theorem is every composite numbers n has a prime factor less than or equal to floor function of root n. Every composite number n has a prime factor less than or equal to floor function of root n. Sir, the before question you asking about prime number, but you are give the theorem about the composite number. Sir, what sir? You may ask the question. Simply I can reply you. So every composite number has every composite number n has a prime factor less than or equal to floor function of root n. This condition fails, definitely the number is a prime number. That's all. If when this condition fail for a composite number, okay, definitely it's a prime number. So first take that number. Okay, check this condition. The condition is satisfied, definitely it's a composite number. The condition fails, it's a prime number. Okay. Proof of the theorem, no need. Okay. Remark. So what I told, that is a remark. If n has no prime factor less than or equal to floor function of root of n, then n is a prime number. Otherwise, it is a composite number. Okay. Don't forget. N has no prime factors. What do you mean by factors? The prime number should be divide the given number with the remainder 0. Okay, then only we call the factors. Okay, so there exists a prime factor less than or equal to floor function of root n. The composite number, no such prime factor exists. That is, it's called a prime number. Okay, we'll see one problem. Determine whether 1601 is a prime number or not. Determine whether 1601 is a prime number or not. Solution. First, list the all prime which is less than or equal to floor function of root of 1601. So root of 1601 is nothing but 40 point something. So floor function of 40 point something is 40. So now I have to list all the prime which is less than or equal to 40. Okay. So try to list out it. Okay. This is a little bit biggest problem. Okay. Even though try to list out it. Okay. So the prime numbers are which is less than 40. The prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37. These primes are less than the number 40. Now, whether these primes, these prime numbers, whether divide the given number or not. The given number is 1601. Whether at least one of the prime divides the given number, it's become composite. So no such prime number divides the given number, it's become a prime number. Okay, please verify yourself. Anyone reply me whether these prime numbers divides the given number 1061. The prime numbers, I have to check the prime which is less than or equal to 40. Okay, divides the given number 1061, 1601. Anyone find the answer? Please reply me. So whether 2 divides 1601, no, not possible. Whether 3 divides, whether 5 divides, whether 7 divides, and so on. Whether 37 divides 1601. Anyone reply me? Any one of the prime which divides the given number? If it divides, the given number is composite. It not does not divide, it's become a prime number. What is your answer? At least tell me whether it is a prime or not a prime, or prime or composite.
Prime, sir.
Prime, prime.
I think so.
So which factor divides?
Uh, uh, no factor divides, sir.
Exactly correct. Good. That is, since none of them is a factor of 1061, verify yourself. Therefore, no, none of the factor divides 1061. Therefore, 1601 is a prime number. This is an important problem. Okay, sometimes 2 mark, 3 mark, 4 marks. Okay, okay, homework. That is, determine whether each is a prime or composite. Number 142, check whether 42 is a prime or composite, whether 129 is a prime or composite, 217, similarly 1001. Okay, check it yourself. Similarly 1729. Okay, my next question, can you find the number of prime number which is less than or equal to the given number? See, in previous problem, whether the given number is prime or not, we can easily check it and we can give the answer. But in this question, please listen, can you find the number of prime numbers which is less than or equal to the given number? Suppose I give 1,000. Okay, find the number of prime number which is less than or equal to 1,000. Is it possible? My question is. Or is there exist any technique? Answer is obviously yes. Okay, that is nothing but next theorem. Before entering to theorem, we see some basic definition. Then only we move on to the theorem. The definition is nothing but a number theoretical function pi of x. Okay, let x be a positive real number. Then pi of x denote the number of primes which is less than or equal to x. So pi of x is called by the number theoretic function. Pi of x denotes the number of primes which is less than or equal to x. Using the summation notation, how do you define pi of x? By using the summation notations. Pi of x can be defined as sum of 1. How long we can sum the value 1? P is lesser, prime number is less than or equal to x. Suppose if we find first prime which is less than or equal to x, I can put 1. So next to prime which is less than or equal to x, I can 1 plus 1, 1 plus 1 plus 1, and so on. This is a simple definition. Okay, from this definition, one thing you have to remember, that is pi of x means denote the number of primes which is less than or equal to x. So this is the result, the theorem. For proving this theorem, or for finding the number of prime which is less than or equal to given number, first you have to find the primes which is less than root n. Then only we can able to find the number of primes. Okay, first thing, I have to find the prime which is less than or equal to root n. Then only I can able to find the number of prime which is less than or equal to the given number. Okay, first step, I have to find the primes which is less than or equal to root n. Then the formula is very simple. You may think that this is difficult. Easily you can remember. Please listen my words. Okay, here the given number is n. You have to find the number of prime numbers which is less than or equal to n. That is ultimatum. For that, first you have to find the prime numbers which is less than or equal to root n, and then keep your mind what are the prime numbers. Okay, the formula is simply, see, the formula start with plus symbol, then alternative symbol, plus minus, first term plus, second term minus, third term plus, fourth term minus, fifth term plus, then sixth term minus, and so on. So alternative symbol you will have. So you have to remember only first 3 terms. The remaining I will teach you. Easily you can remember. Only you have to remember first 3 terms. The first term is n. The next term is minus 1. The third term is pi into pi of root of n. That is number of primes which is less than or equal to root n. If we know this thing, then only we can able to evaluate this thing. Okay, that is the number of primes which is less than or equal to n, the formula is n minus 1 plus pi of root of n minus. After this, all are same type. That is, first you have to put the floor function, okay? Then n divided by single primes. So what we did in principle of inclusion exclusion. Suppose I choose a single sets mod A, mod B, mod C, then A union B, A union C, A union D, and so on. After that, A union B union C. So collection of single set, collection of two set, collection of three sets, and so on. Similarly here, first I have to collect the floor functions of n divided by single prime. Floor functions of n divided by single prime. The next one, n divided by 2 primes, collection of 2 primes, okay? All the collection of 2 primes. The next one, n divided by collection of all 3 primes, collection of n divided by collection of all 4 prime, 5 prime, and so on. So first I start with plus symbol, next minus symbol, third plus symbol, minus symbol, and so on. First 3 terms, n minus 1 plus pi of root n. After that, floor function of n divided by single prime. So collection of floor function of n divided by single prime. Then collection of floor functions of n divided by 2 primes, and so on. Easily you can draw by the formula. Proof, no need. Problem 1. So find the number of primes which is less than or equal to 100. This is an important problem. Okay, find the number of primes which is less than or equal to 100. Okay. So what I told, find the number of primes which is less than or equal to 100. First we have to find the prime numbers which is less than or equal to root of 100. Then only we can able to find number of prime which is less than or equal to 100. Okay. So my first step is, here n is 100, given number is 100. So first step is I have to find the pi of root n. That is pi of root 100. That is pi of 10. What is our pi of 10? Pi of 10 means number of primes which is less than or equal to 10. Easily you can calculate number of primes which is less than or equal to 10. 2 to 10, how many primes you have? 2, 3, number 1, 2, number 2, 3, number 3, 5, number 4, 7. So there are 4 primes which is less than or equal to 10. So pi of 10 value is 4. Okay. What are there? The 4 primes which is less than or equal to 10 are 2, 3, 5, 4. So here I have to collect the collection. So single 10, single 2, single 3, single 5, single 7. Then next 2, 3, 2, 5, 2, 7, 3, 5, 3, 7. After that, fix the first 2 integers, 2, 3, 5, 2, 3, 7. Then leave the 3 integer, 2, 5, 7. Next 3, 5, 7. Finally 2, 3, 5, 7. So principle of inclusion exclusion. In that formula, how do you collect the 2 sets? How do you collect 3 sets? How do you collect 4 sets? Similarly here, how do you collect 2 numbers? How do you collect 3 numbers? How do you collect 4 numbers? Okay. Then call them P1, P2, P3, P4 respectively. Okay, then by previous theorem, there is nothing but theorem. We can recall the theorem. So what's the theorem? P1, P2, Pt are the prime numbers which is less than or equal to root 10. Then we have a formula. Okay. Okay, just write the formula. Okay. Pi of, see, listen, pi of n, where n is 100. So here I write pi of 100. Okay, then n is 100 minus 1 plus pi of root 100. Pi of root 100 is nothing but pi of root 100 is nothing but 4. Okay, so my answer is, so this is n, this is minus 1, always minus 1. This is pi of root 100. There is nothing but pi of 10. That is nothing but 4. Then plus minus plus minus. So floor function of given number is 100. The prime numbers are 2, 3, 5, 7. So floor functions of 100 by 2, 100 by 3, 100 by 5, 100 by 7. This is first collection. So why I put the bracket? Because all the collection you have a minus symbol. So see, in the previous problem, don't think that only for n by pi, single pi, there is no minus. For such collection of n by single pi, For that collection, you have minus symbol. You don't think that, sir, you said alternate symbol. So I put first n by pa minus 1. For next n by pa, I put plus. That is not correct. Okay. Here plus, minus, plus. For collection of single, that is n divided by single pa, always you have minus. The collection of n divided by 2 PAs, always you have plus symbol. Collection of n divided by 3 PAs, you have always minus. So only here I put bracket. Okay. So this is collection of all single PA. That is 100 flow function of 100 divided by 2, 100 divided by 3, 100 divided by 5, 100 divided by 7. The next collection 2 prime. So for the collection I have to put plus, because plus, plus, minus, here now I have plus. So what are the two collection? 2 3, 2 5, 2 7, then 3 5, 3 7, then 5 7. So there are 6 numbers. Okay. After that, collection of 3. How do you easily you can say that from out of 2 3 5 7, first fix 2 3. Okay. Then bring the third number. So 2 3 5, 2 3 7. Okay. Next leave the 3 number. So 2 5 7. Finally 3 5 7. Already I told you. So try to write it. Another option. 2 3 5 7. So first I keep 2 3 is constant. So from this I can add 5, I can add 7. So 2 3 5, 2 3 7. Then I leave 3. Now I collect the 3 numbers 2 5 7. Then I can leave 2. Now I collect the remaining 3 numbers 3 5 7. Okay. So such collection is 4 collections. Okay. After that, plus 100 divided by 2 into 3 into 5 into 7. Now easily you can evaluate. You know how do you evaluate these things, and evaluate it. Finally I get 25. So the answer is 25. That is 25 prime numbers which is less than or equal to 100. We have a 25 prime numbers which is less than or equal to 100. Okay, homework. Compute the number of prime which is less than or equal to n. So first one 47, 61, 96 and 131 and so on. Okay. So the next thing, can you find the maximum distance of any two consecutive prime numbers? See, suppose consecutive prime numbers means 2 3 are consecutive prime number, 3 5 are consecutive prime numbers, 5 and 7 are consecutive prime numbers, then 7 and 11 are consecutive prime number, 11 and 13 are consecutive prime numbers. Can I define a maximum distance of any two consecutive prime numbers? The question. In other words, for a given length n is a positive integer, can you find the consecutive composite number? Suppose I give a length 10. So can you find the consecutive 10 composite number? Suppose I give the 100. Can you find the consecutive 100 composite number? Did you understand my question first of all? So if you want to define the distance, that can you define a maximum distance of any two consecutive prime numbers? This is my question. In other words, see, if not possible, suppose if it is possible means the maximum distance possible means the second question is stopped with some integer n. The first question is the answer is no means in the second question n may be infinite. N may be infinite. That is n you can take 1 lakh, 2 lakh, 1 crore, 2 crore and so on. Can you understand my question? That is my depends on the first question. You have the answer for the second question. What is my first question? Can I define a maximum distance of any two consecutive prime numbers? அதாவது ஏதாவது ரெண்டு நம்பர் prime number எடுத்துக்கிட்டீங்கன்னா அதுக்கு அதோட கேப்னால டிஃபைன் பண்ண முடியுமா? ஃபார் எக்ஸாம்பிள் maximum distance between 7 and 5 எவ்வளவு? only one number. Okay. Similarly, அதே மாதிரி தான். Okay. So in other words, for a given length n, can you find the consecutive composite number? Suppose we cannot define the maximum distance. We cannot define a maximum distance means for each and every n, we can able to find the length n of consecutive prime numbers. We can able to find the length and n of consecutive. Suppose we can find 10 consecutive composite number, 100 consecutive composite number. The first answer is yes, means that is maximum distance possible, means the second question automatically fails. Only fixed n only we can able to find. Okay. Look, is that exist any technique for the above one? That means the answer for first one, there is no possible of defining maximum distance of any two consecutive prime number. Okay, because we cannot find the distance between any two prime number, because prime numbers are infinite numbers. If you fix the prime number, this is last prime number, means we can able to find the distance, but the prime numbers are infinitely many, so we cannot fix it. So in that case, the answer for first question is no. Obvious, that means obviously the second question will satisfy, because there is no possible of defining the distance between two consecutive numbers. So there is a possible of defining, there is a possible of finding consecutive composite number whose length is any n, where n is a positive integer. There exists any technique for the above one? That is, can you find the consecutive composite number for given length? Is any techniques there? The answer is yes. This is also an important problem. So we see the theorem. For every positive integer n, there are n consecutive integers that are composite number. If you take any positive integer, definitely there are n consecutive integers that are composite number. Suppose if we give any positive integer 100,000 lakh, we can able to find consecutive 100 positive integer, 100 composite number, consecutive 1000 composite number, consecutive 1000 1 lakh number, 1 lakh composite number, and so on. Okay, proof of the theorem no need. Okay, but what is the technique? That is I given in the remark. The n consecutive, suppose n is given, I have to find the 10 consecutive positive integer, means my n is 10. Okay, suppose I want to find the 10 consecutive positive integer, means the n is 10. What's your formula? See, the formula start with n plus 1 factorial plus 1 plus 2, sorry, n plus 1 factorial plus 2, and n with n plus 1 factorial plus n plus 1. Okay, so the suppose n is 10, means I start with 10 plus 1 factorial plus 2 and n with 10 plus 1 factorial plus 11. Start with plus 2, n with n plus 1. Don't forget. So because all the in all the term we have n plus 1 factorial is common. So suppose you want to need n consecutive integer, the formula is n plus 1 factorial plus 2, n with n plus 1 factorial plus n plus 1. Suppose I want 10 consecutive integer, means I start with 10 plus 1 factorial plus 2, 10 plus 1 factorial plus 3, and so on. I end with n plus 1 factorial plus, that is 10 plus 1 factorial plus 11. So when you check it, these all 10 numbers are composite number. All n numbers are consecutive composite number. What do you mean by consecutive integer? 2, 3 are, when you say consecutive integer, the difference is 1, we can say that consecutive integers. Definitely this is some number plus 2, this is same number plus 3, definitely the difference is 1. Okay, this is one of the important problem. Okay, in next class, so time is over, so next class we will see the problem. This is an important problem, 6-mark problem. Find the 6 consecutive integers that are composite. That means I have to find 6 consecutive composite number. What is the answer for the given one? I have to find the 6 consecutive composite integers. Okay, we will see this in the next class. Okay, because time is over. Now you can leave the class.